So let's do some of these projections. We're going to start off with an inner product on polynomials of degree 2 or less that samples 3 points, -1, 0, and 1. Okay? It's symmetric. I have -1, 0, and 1. I could have used -2, 0, and 2, or -5, -4, 4, and 5. All of those are going to be symmetric. The advantage of using a symmetric inner product is that not just symmetric like Q with P equals complex conjugate of P with Q, but symmetric in the sense that it uses negative numbers and positive numbers, is that the inner product of an even function with an odd function will automatically be 0 if I do this. Okay, and that's because over here, the odd function will be negative. The even function won't care. Over here, it'll cancel. And at 0, the odd function will obviously give me 0. Okay? So what we're going to do is we're going to project the function cosine pi t onto this space. Okay? So we need an orthogonal basis. We're going to start with 1t and t squared. The inner product of 1 with t is 0, because 1 is an even function, t is an odd function. The inner product of t with t squared is 0, because t squared is an even function, t is an odd function. But 1 with t squared, well, what's that going to be? 1 times 1 plus 1 times 0 plus 1 times 1. That's 2. So what we're going to do is we're going to make an orthogonal basis by subtracting. Okay? So what I'm going to do is make use of the fact that the projection of t squared onto the space span of 1 and t, if I do the difference between that and t squared, I get something that's orthogonal to 1 and t. So I'll use t squared minus the inner product of 1 with t squared is 2, divided by the inner product of 1 with 1, which is 3, times 1. Okay? Now, these are not normalized. So let's make them normalized so we don't have to worry about it. The inner product of 1 with itself is 1 times 1 plus 1 times 1 plus 1 times 1, which is 3. So I have to divide by the square root of that. Okay? Here, what about the inner product of t with itself? Well, that's going to be -1 times -1 plus 0 times 0 plus 1 times 1. That's going to be 2. So I need to do this divided by the square root of 2. How about the inner product of this with itself? Well, it's going to be 1 minus 2/3, that's 1/3, times 1/3 is 1/9. 1/9 plus -2/3 times -2/3, so that's 4/9. So I've got 5/9. And then here, so that's going to be 1/3 times 1/3, that's 1/9. So that's 6/9 or 2/3. So I'm going to multiply here by the square root of 3/2. All right? Now let's see what these look like. This is our orthonormal set of polynomials. All right, that's what they look like. You can see from this diagram why I don't want to use the word perpendicular. All right, that wouldn't make any sense to say, oh yeah, these polynomials are perpendicular. Yeah. Anyway, they are clearly orthogonal with respect to our inner product. All right, so let's try projecting cosine of pi t. Okay, cosine of pi t is an even function. An even function. So that means that its inner product with P1 is 0 because P1 is odd. You do this projection, what you'll get is minus 1/3 P0. Well, actually, I renormalized, so let's go ahead and do this again. All right? I'm going to take f of t as cosine pi t, so I don't have to write it a bunch of times. And then I'm just going to do the inner products. So what is P0 of -1, f of -1, plus P0 of 0, f of 0, plus P0 of 1, f of 1. -1 over the square root of 3. Okay? So I'm going to do my projection as -1 over the square root of 3 times P0. What about with P2? Well, happily, I only have to change these numbers. And I get -2 times the square root of 2/3. Let's see what that looks like. All right. So that's going to be our projection. And let's plot cosine pi t and this projection. All right. So according to this inner product, the orange quadratic is the closest function in all of P2 to the blue function. Now, it might not look very good to you guys, but notice that as far as our inner product is concerned, it's exact. You see, it works at -1, it works at 0, it works at 1. Those are the only points that have any weight at all for our inner product. So as far as the inner product that we're using is concerned, the orange function is equal to the blue function. There's no difference at all because they have exactly the same values at the only points of interest. Okay. Now, of course, we might think that that looks like a pretty shoddy approximation, and I wouldn't blame you. But if you want a better approximation, you should employ more points. So let's see what happens if instead of just using the points -1, 0, and 1, what if we use the whole set of points between -1 and 1? That again will allow us to take advantage of symmetry. We're going to integrate from -1 to 1. Okay? So I've already done that down here, defining some functions. The way that I did this was I said, let's start with 1. What's the inner product of 1 with itself? Well, it would be the integral from -1 to 1 of 1 squared dt. That's obviously 2. So I divide by the square root of that in order to normalize. Same thing here. The integral from -1 to 1 of t times itself dt is 2 times 1/3, or 2/3. So I divide by that or multiply by the square root of its reciprocal. I didn't have to worry about subtracting there because t is an odd function, 1 is an even function. So the inner product of 1 with t is automatically 0. In order to do t squared, I had to do this. T squared minus the integral of w0 of t, or I need to use a different letter here. So I'm going to use x times x squared from -1 to 1. So this is the inner product, w0, with my new vector. And then I have to multiply by w0 of t. I would also have to subtract for w1, But because t squared is even, that's going to be 0. If I do that, I get t squared minus 1/3. Then I integrate t squared minus 1/3 times itself, -1 to 1, and I get 8/45. What did I do? Square root of 45 divided by 8. Okay? T squared minus 1/3. Let's not talk about W4 yet. All right, now, how will I get my coefficients? Well, I'm going to integrate W0 of d cosine pi t from -1 to 1. And that gave me 0. Okay? So that means that there is no W0 component in this expansion. What about W1? Well, cosine pi t is an even function. W1 is odd. So that one's going to be 0 automatically. What about W2? Minus 3 times the square root of 10 divided by pi squared. Well, that's surprising. All right, so I'm going to use a projection here. Get rid of this because we don't need that yet. All right? And it's going to be minus 3 times the square root of 10 divided by pi squared times W2. Let's see what that looks like in our graph. Okay, and I'm just going to go from -1 to 1. First, let's look at what that would look like. All right, once again, it's exact as far as the old inner product was concerned. But let's see what capital projection looks like. Ready, set. Well, so green, it's better. It compromises on 0, -1, and 2, shifts the thing down a little bit. But you see how in aggregate, it's closer to blue than orange is. All right, in aggregate. Because that's what this inner product values. All the numbers between -1 and 1. All right? So now I could ask, how good is it? To answer that question, I'm going to need to use something called Bessel's inequality.